Hello everyone! In this lesson, we will continue to study the frequency domain analysis module of continuous system. Today, we will study the frequency domain analysis method of continuous system, mainly discussing the frequency domain analysis method of LTI system. The main contents include convolution theorem, frequency domain analysis method of LTI system, and the application of convolution theorem. First, let's review the convolution theorem. Convolution theorem is divided into convolution theorem in time domain and convolution theorem in frequency domain. Convolution theorem in time domain means that convolution of time domain functions can be expressed by product of spectral density functions, as shown in Formula 1. The convolution theorem in frequency domain refers to the product of time functions can be expressed by 1 over 2 pi times convolution of two spectral density functions, as shown in Formula 2. The convolution theorem reviews the operational relationship between time domain and the frequency domain. In the field of communication system and signal processing, it has been widely used. Let's discuss the frequency domain analysis method of LTI system. We should use the concept of frequency response function. From the time domain analysis of system, we know that for a linear time invariant system, if the excitation signal is ft, the zero-state response of the system is yzst, then yzst is equal to the convolution of ft and the unit impulse response ht of the system, as shown in Formula 3. In other words, the zero-state response of the system, the input of the system, and its unit impulse response form a convolution operation. According to the convolution theorem in time domain, we can find that the spectral density function of the zero-state response of the system is equal to the spectral density function of the input signal times hj omega, where hj omega is the Fourier transform of the unit impulse response of the system. In engineering, hj omega is called frequency response function or system function. It is expressed by Formula 5, that is to say, the system function hj omega is equal to the spectral density function of the zero-state response yzsj omega over the spectral density function of the input signal fj omega. Based on the previous analysis, we can get the basic steps to solve LTI system by frequency domain method. Step 1. Find the Fourier transform fj omega of the input signal ft. Step 2. Find the system function hj omega. The system function is actually the Fourier transform of its unit impulse response. Step 3. Find the Fourier transform of the zero-state response yzst. According to Formula 4, we can find the Fourier transform of the zero-state response yzst by multiplying the spectral density function of input signal and the system function. Step 4. If we need to solve the time domain output of the system yzst, we can take the inverse Fourier transform of yzsj omega. In this way, we can convert time domain response into frequency domain response. It's very important to find the system function hj omega. Besides the Fourier transform of ht, there are other ways to find hj omega. Let me show you an example. It is known that the differential equation of an LTI system y double prime t plus 3y prime t plus 2yt is equal to f prime t plus 2ft. Question 1. Find frequency response function hj omega of this system. Question 2. If the input ft of this system is equal to epsilon t, find yz j omega. That is to say, you need to find the spectral density function of its zero state response. First, we can find the frequency response function according to the differential equation. The method is very simple. According to the differential characteristic of Fourier transform, we can find the Fourier transform of the two ends of the equation, as shown in Formula 6. Here you should know that when you are finding the Fourier transform of y double prime t is multiplied by the square of j omega. In the same way, y prime t is multiplied by j omega. And at the right end of the equation, f prime t also needs to be multiplied by j omega. Therefore, we get Formula 6. It can be expressed by Formula 7. We extract yz as j omega on the left and fj omega on the right. Then, according to the definition of system function, hj omega is equal to yz as j omega over fj omega, so we can get Formula 8. Let's look at the second equation. Because the input ft of the system is equal to epsilon t, and we solve the Fourier transform of epsilon t as shown in Formula 9. That is to say, fj omega is equal to pi delta omega plus 1 over j omega. Then according to Formula 8, we can get the output of the system yz as j omega is equal to hj omega times fj omega, as shown in Formula 10. From this example, we can find that when we solve the frequency response function hj omega of the system, we can also get hj omega by calculating the Fourier transform on both sides of its differential equation. Let's look at another example. There is a system as shown in Figure 1. It's known that the input of multiplier is ft. Ft equals sine 2t over t. The other input, st, is equal to cosine 3t. The frequency response function hj omega of the given system is shown in Figure B. Well, what is the function of the system shown in Figure A? As shown in Figure A, in this system, ft is multiplied by st. The product enters a low-pass filter. Finally, the output yt of the system is generated. Here, hj omega is a low-pass filter. Why? Let's take a look at its spectrum. The highest cut-off frequency of hj omega is 3. When the frequency is more than 3, its amplitude frequency characteristics becomes 0. So it's a low-pass filter. Let's analyze the working process of this system. This is the diagram of the given system. The input signal cosine 3t and sine 2t over t enter the multiplier. After they are multiplied by each other, we get its output xt equals st times ft. According to the Fourier transform, we can find that the spectrum of xt is xj omega. The spectrum of xj omega is shown in Figure B. Let's look at the two inputs of the multiplier. ft is equal to sine 2t over t. It can be expressed by 2 sine 2t over 2t. Then ft is a sampling signal, and a spectrum must be a gauge function. Through further solution, we can see that its spectrum is a gauge function with a width of 4. We have learned that after ft is multiplied by cosine 3t, there appears spectrum shifting. The result of its spectrum shifting is that the original gate is shifted to 3 and minus 3. Through such an analysis, it is not difficult to understand the spectrum of xj omega. Then xt gets its output yzs after passing low-pass filter. For this low-pass filter, its input is xj omega, its output is yzsj omega. So yzsj omega is equal to hj omega times xj omega. This is the result of convolution theorem in time domain. From this spectrum, we can find that through such a low-pass filter, signal whose frequency is higher than 3 and signals whose frequency is lower than minus 3 are filtered out. Therefore, we can get the spectrum of the system's output yzsj omega. If you want to analyze the output of this system in time domain, you only need to take the inverse Fourier transform of yzsj omega directly. Let's take a look at specific solution steps. For question 1, first, we need to find x and its spectrum, because xt equals st times ft. So according to the convolution theorem in frequency domain, xj omega should be equal to 1 over 2 pi times the convolution of fj omega and sj omega. Here, st is equal to cosine 3t. ft is equal to sine 2t over t. Therefore, if we want to find the spectrum of xj omega, we must know the spectrum of cosine 3t and sine 2t over t. Let's review an expression. You have learned that the Fourier transform of the gauge function is tau as a omega tau over 2. We can transform it into other form. If tau is equal to 4, then according to the symmetry of Fourier transform, we can get the corresponding spectrum of 2 sine 2t over t is 2 pi g4 minus omega. Because the gauge function is an even function, so it can be denoted by 2 pi g4 omega. 2 in the equation can be removed, so the spectrum of the given function sine 2t over t is equal to pi g4 omega. St is equal to cosine 3t. According to what we learned before, obviously, its spectrum should be pi delta omega plus 3 plus delta omega minus 3. Then, replace fj omega and sj omega in the first formula. We can get formula 11. Here we can find that the spectrum xj omega also has 2 gates. The width is 4, and they are moved to minus 3 and 3 respectively. Next, let's find the output yzsj omega of this system and its time domain function yzst. According to the characteristics of the system, yzsj omega is equal to hj omega times xj omega. The given system function is a gauge function with a width of 6. So if we multiply these two functions, we can get formula 12. This is the spectral density function of the system output. By observing formula 12, we can find that the output yt of the system is equal to sine t over t times cosine 2t. Why? According to the convolution theorem in frequency domain, in such a convolution theorem, it's obvious that the latter term is a spectrum of cosine 2t, and the former term is the spectrum of sine t over t. So it can be denoted by yt equals sine t over t times cosine 2t. This is the spectrum of yz as j omega. Usually, when performing its related operation with the help of its graph, we can calculate its corresponding result more accurately. This is the spectrum of xj omega. This is the spectrum of the system hj omega. Obviously, after two gates pass low-pass filter, we still get two gates, but they are narrower than before. Through the explanation and the analysis of these two examples, I hope you can master the basic steps for solving LTI system by frequency domain methods and determine the frequency response function of the system from differential equation, and master the convolution theorem and its applications. So much for today. Thanks for your listening. Goodbye.